So to continue our look at supporting students who are struggling in learning math, let's move on to those students who are struggling with math-specific issues. So we talked about students who may have some attention or executive function challenges that impact math, students who have language processing problems that impact math. But let's look at those students who have math-specific challenges. Uh, Particularly those students with developmental dyscalculia. To help those students, we've got a few tools in our toolbox. So the first is to find ways to reduce overall cognitive load. So certainly the advice I gave for reducing the impact of language and impact of attention demands will help a student who has dyscalculia, even if they have no underlying weaknesses with attention and language processing. And in particular to those students who have comorbidity, which does tend to occur for many students with those other diagnoses. So finding ways to reduce the overall extraneous load will help all students, but particularly those students with dyscalculia. Finding ways in particular to reduce the decoding demands that are associated with new symbols, new language, and working on those separately from the concepts and the procedures is helpful for a lot of students who have developmental dyscalculia, and for that the use of visuals and manipulatives is key. So we'll talk a little bit about how manipulatives in particular can help a student both understand a concept and work through a procedure without needing specialized language, without needing to have an automatic and fluent decode number sense. And through a reduction of both the intrinsic and the extraneous load that they're struggling with. And finally, we want to find ways to help students express their knowledge, show that they understand a mathematical concept, even if they may struggle with applying a mathematical procedure or using the correct language around it. So while those elements are important and have a place in the math classroom, I think we need to recognize and value students who are able to understand those concepts and understand them at a deep level. In this lesson, you saw the profile of Dr. Emma King, who, if we focus purely on her arithmetic skills, would not have had the opportunity to achieve a PhD in cosmology. I was working at a community college a year or two ago, and I presented that profile to a group of mathematics teachers I was working with, and one of them raised his hand and he said, I have a student exactly like that. He's taken our remedial math non-credit community college course 3 times and failed it every time. But I've sat down with him and we've looked at some very complex calculus concepts, and he understands them better than any other student I know. And yet at the same time, I can't get him into my calculus class because he can't pass the non-credit remedial math class. So clearly we don't always have control over these system-wide challenges, but finding ways to help students understand that they have real strengths in math, and they can build on those strengths, can address some of the affective elements that come with struggling in a traditional math classroom. So let's look at a few examples for how we can actually implement this. I'm gonna mostly focus on manipulatives because I think it's a great tool, and it's a tool that can help us both with the conceptual and the procedural aspect of supporting students who learn differently. Uh, so, so for example, let's think about helping students understand the concept of a variable. So here, I'm going to use a representation of a variable. I'm not going to rely on heavy abstraction. So what I'm going to do is keep a one-to-one correspondence between the elements I'm using as manipulatives and what I'm representing. Uh, so you can see on this side of my equation, I have two, Easter eggs that are closed. So there are a certain number of these sort of red squares in there, and um, I don't know how many are in there, but I do know that all the eggs that have the same color will have the same number of pieces in them. So there's the same number in this egg as this egg, but I don't know how much is in each of these eggs. I also know that on this side of my little board, I have 4 red squares, and that whatever is in these 2 eggs is equal to these 4 red squares. So I can then open these red squares and reveal that that in fact I have an equal amount in each, and that I have 2 in each, and that this total number does indeed equal that number. Uh, uh, so you could use this as a way to assess knowledge. So you could ask students to predict what quantity is in these eggs ahead of time. So they're solving for that variable. And they can confirm their whether or not their solution is correct by actually opening the eggs and seeing how many are in each. So there's a physical one-to-one representation of each of the elements that they can confirm in person. So that concrete representation can then be bridged to a one-to-one corresponding abstract representation. So here I'm going to create an equation showing that on this side I have 2 boxes, and I don't know what's in these boxes, but I know that they're the same kind of box, so they're going to contain the same quantity. And on this side I have 4, and in this case I'm representing negative numbers, but I have 4 quantities that are being represented, and I can then represent that as half of these are going to be in one box, the other half will be in the other box. So if I want to look at what's in one box, it's only 2 of these negative elements. And that can then be bridged onto a fully abstract symbolic representation. So here I have 2x, and that represents my 2 unknown quantities, or my 2 hidden eggs. And I know that these 2 x's are equal to -4, so these negative objects that I have. And therefore, if I split this -4 equally, divide it by my 2 x's, then each x represents -2. So here we go from a concrete one-to-one representation to an abstract representation to a symbolic representation to bridge that algebraic concept. Let's take a look at another example. So I'm going to look at a linear equation. And now I'm going to look more at a procedural support because we're going to do a bit more abstraction. So these are common algebra tiles, but rather than using one-to-one correspondence, I'm now going to start pushing my students to work a bit more abstractly. And what I'm going to push them to do is to consider this green line to be x, an unknown variable. And these white tiles are positive numbers. So on this side of the board, I have one unknown variable and 6. And on this side, I have three x's. These are all the same variable, plus 4. So the question is, what's x? So what I can help them do is work through a procedure. So understand that to isolate x on its own on one side of the board, what I need to do is subtract 4. So I'm adding -4 tiles to both sides of the board. And the positives and negatives cancel out. So now I have 3 x's on one side, x plus 2 on the other. I subtract x from both sides, and what I find is that I have 2 x's on one side, 2 tiles on the other, and clearly that means that x must be 1, because I split these equally, divide these equally between my remaining x's. So here I don't have eggs with the tiles in them that allow me to double check. I have to abstract what the variable is. This is x, but I'm working through the procedure I would need to solve this algebraic problem. And again, that can be bridged to a representational format, and then finally to the fully symbolic format, or straight to the symbolic format once students are comfortable with that representation. So I started with 3x plus 4 equals x plus 6. I subtracted 4 from both sides. That gave me 3x equals x plus 2. I subtracted x from both sides. That gave me 2x is equal to 2. I divided my 2 equally between the 2 x's, and I got x is equal to 1. So clearly here I've chosen things that I can neatly work through with the students. But as students develop proficiency, you can increase the complexity of the problems they deal with. And once they're fluent enough with working with symbols and numbers, assuming that they don't have an underlying challenge such as developmental dyslexia that may prevent them from becoming fluent in working with symbols and numbers, you can then transition them to a fully abstract. And for students who struggle with that, stick with the manipulative representation, because that's easily translated into the sort of a fully symbolic representation most of the time. And there's a wide range of manipulative tools and virtual manipulatives that are available and accessible to students to help them learn a wide range of mathematical concepts and approaches.